Have you ever stopped to think about what actually happens in that tiny split second after you click on a link? I mean, it feels like magic, right? Well, it's not. In this explainer, we're going to trace that single click on its incredible journey from your screen out through your local network and all the way across the globe.
So here's our game plan. We're going to follow a single piece of your data through 5 key stages. First up, we'll see how your device gets its digital identity. Then, how it finds its way around your local network. After that, it's the big journey across the internet, and we'll look at the digital security team that keeps it safe. And finally, how the whole system keeps all that traffic moving without grinding to a halt.
You know that click feels instantaneous, but behind that incredible speed is this really complex, elegant dance between hardware and software. It's a journey that's governed by a very precise set of rules, and we're going to follow just one piece of data step by step to see exactly how it all works. All right, first things first. Before our little data packet can go anywhere, your device, whether it's your phone, your laptop, whatever, it needs a unique identity on the network. You can kind of think of it like needing both a passport and a mailing address. It actually needs 2 different kinds of addresses just to get started. So your device juggles these 2 different addresses. The first is the MAC address. This is permanent. It's literally burned into your device's hardware. It's like a serial number that never changes. The second one is the IP address. This is more like a temporary mailing address that gets assigned to you whenever you join a new network. Can you imagine having to manually type in a new IP address every single time you connect to Wi-Fi? It would be a total nightmare. Thankfully, we don't have to. There's a protocol called DHCP, that's Dynamic Host Configuration Protocol, that handles all of this automatically. Your device just connects, it asks for an address, and the network's DHCP server hands one over. It's really that simple. And that brings us to another layer of convenience. Because let's be honest, we humans are not great at remembering long strings of numbers, like an IP address. We like names, right? Google.com. That's where DNS, the domain name system, comes into play. It's basically the internet's phone book. It translates the simple names we type into the IP addresses the network actually needs to find the website. Okay, so our device has its addresses and it knows where it wants to go. But before it can hit the big internet superhighway, it has to navigate its own local neighborhood. That's your home or your office network, also known as a LAN. And this is where a couple of key pieces of hardware take over. Now, this slide shows 2 absolutely critical devices. The switch is the one that handles all the local traffic. It connects devices on your network, say your laptop to your printer, using those permanent MAC addresses. The router, on the other hand, is the gateway to the outside world. It connects your entire local network to the internet, and it uses IP addresses to send your data on its global journey. So think of it this way. The switch is your local mail sorter, and the router is the cross-country truck. Now, in bigger places, like an office, networks are often organized using something called VLANs, or virtual LANs. It's a really clever way to create separate digital networks using the exact same physical hardware. So, for example, you can totally isolate the accounting department's traffic from the marketing department's. This is fantastic for security, and it also boosts performance by cutting down on all that unnecessary network chatter for everyone. Okay, our data packet has officially left the router. It is now out on the open road of the internet, which is really just a massive wide area network, or a WAN. And for this global journey to work at all, everything has to play by the same rules, a standard, agreed upon framework. And that framework is called the OSI model. Now, I know this looks really complex, and well, it is. But the key thing to get here is that it breaks down the huge job of network communication into 7 distinct layers. Each layer has one specific job to do, from sending electrical signals over a wire at the very bottom, all the way up to formatting data for the app you're actually using. This layered approach is what lets devices and software from literally anywhere in the world communicate with each other seamlessly. Now it's time for a little bit of internet magic called NAT, or Network Address Translation. See, your internet provider only gives your home one single public IP address. But you've got a laptop, a phone, a smart TV. How do they all get online? Well, NAT, which is handled by your router, cleverly translates the private IP addresses of all your devices into that one public IP, letting everyone share the same connection. You know, it helps to think of the internet not as one single network, but as a network of networks. And BGP is the protocol that directs traffic between these massive independent networks. It's basically the air traffic control system for the entire internet. constantly calculating the best and most efficient paths for data to travel across the globe, which keeps everything stable for all of us. So, our data packet is flying across the public internet. How on earth does it stay safe? Well, it doesn't travel alone. It has a whole digital security team working around the clock to protect it from all sorts of threats along the way. First up is the firewall. You can think of it like a security guard standing at the front door of your network. It inspects every piece of traffic trying to come in or go out, and it checks everything against a set of security rules. If anything looks suspicious or just isn't on the approved list, it gets blocked. It's your first line of defense against attacks. Next in the security detail is the VPN. Using a VPN is kind of like sending your data packet inside a private armored car. It creates this encrypted tunnel between your device and a remote server, completely hiding your online activity from any prying eyes. This is absolutely crucial when you're on a public, untrusted network, like the Wi-Fi at your local coffee shop. And then you've got the proxy server. This one acts like a middleman. You send your request to the proxy, and then the proxy goes out and forwards that request to the internet for you. So, why would you do this? Because the website you're visiting only ever sees the proxy's identity, not yours. It's really useful for masking your location or getting around regional content filters. This table really sums it up nicely. You can think of it like this. A firewall is the bouncer for your whole network, checking IDs at the door. A VPN is your personal bodyguard, protecting your data with heavy-duty encryption wherever you go. And a proxy server is your disguise, letting you appear to be somewhere you're not. They're 3 different tools for 3 very different security goals. All right, for our final section, with billions and billions of data packets flying around the internet at any given moment, how does the whole system avoid becoming one giant digital traffic jam? Let's look at how the network manages all this traffic to make sure we get a smooth, fast experience. This is managed by something called Quality of Service, or QoS. What QoS does is it basically creates a high-occupancy vehicle lane on the internet highway. It gives top priority to time-sensitive stuff like a video call to make sure it gets through without any lag. Meanwhile, less urgent traffic, like a background file download, is told to take the slower lane. But what about really popular websites that get millions of visitors at once? They use things called load balancers. See, when you go to a site like Google or Amazon, you're not actually connecting to a single server. A load balancer acts like a traffic cop, and it directs your requests to one of many identical servers, spreading out the workload so no single machine ever gets overwhelmed. And this is exactly why those major online services are so incredibly reliable. Load balancing is really the key to their stability and their performance. It lets them handle huge spikes in traffic, it makes sure the service stays online even if one server goes down, and it provides a much faster experience for every single user. And that completes our data packets journey. We saw it get its addresses, navigate its home network, and cross the entire internet guided by this complex web of rules. We saw how it's protected by digital guardians and kept moving smoothly by traffic management systems. The whole thing is built on these interconnected layers of technology and trust. It really makes you wonder, which one of those layers is the most important? What's the one piece of this whole puzzle that we just can't afford to break? Something to think about the next time you click.